Okay, so here we are in the home stretch. We've got a week left, basically. So there's a few things I want to tidy up. We started studying algorithms for a bit, then we kind of jumped into Java, and there's some loose ends with our study of algorithms that I want to tidy up. But before that, if anybody has lost a watch or needs a watch, one has been found, so it's up here. So I want to get back to doing a couple of things today. One is recursion and good ways and bad ways to use it. So we'll see one bad example of recursion and another really good example of recursion, and how that ties into to our study of algorithms. So here's something that was on an assignment. Fibonacci numbers. So the nth Fibonacci number, how is that defined? Never heard of Fibonacci numbers before? You've done some generalization of them on assignments. So the nth Fibonacci number is given by a formula, which is Fibonacci of n is equal to Fibonacci of n minus 1 plus Fibonacci of n minus 2. So it's a recursive formula. And there's a couple of base cases, Fibonacci of 0 and Fibonacci of 1. They're both equal to 1. Okay, so that's the definition of Fibonacci numbers. And the definition is recursive, so it's natural to implement them recursively. So we know what the base cases are. If n is less than or equal to 1, we'll return 1. And otherwise, we'll return Fibonacci of n minus 1 plus Fibonacci of n minus 2. Okay? So these numbers were invented by this guy, Fibonacci, some time ago, as a model of the reproductive behavior of rabbits. So they get big pretty quickly. We can test this out. So let's check our base cases. Fib of 0 is 1, fib of 1 is 1, fib of 2 is 2, 3 is 3, 4 is 5, 6, and if I do 20, I'm all the way up to 10,000, and if I do 50, it takes a little while. So these Fibonacci numbers take some time to compute this way because they're kind of big. So maybe we don't want to wait for 50. Let's try 51, or not 51, 21, 22, 23. You think we can do 40 quickly? Not so quickly. So somewhere it starts to get out of hand, and we can do binary search to find out where. So 32 is still okay. 33 is a little bit slower. And now we're starting to take some time. It's noticeable delay. And these numbers here, fib of 35 takes a few seconds to compute, and it is it's 1.5 million roughly, so 1,490,000 or so. That's not such a big number. I mean, we can do lots of things. It's not that the fact that the number is so big that it's taking a long time to compute. It's more to do with the way we're computing it. So if we look at this function that we wrote, we can try running it, we can try tracing its execution on a few small examples, and maybe we can understand what's happening here. So let's try. Let's do maybe, I don't know, fib of 4, let's say. That's an easy one. So fib of 4, if we call that function, we get a stack frame in which n equals 4. And then what happens?
See, is it n less than or equal to 1?
Yep, so we compare n to 1, and n is not less than or equal to 1, so we skip the return statement and move on to the next line. And what happens?
Fib 4 minus 1 is less.
So we call fib of 3. So we call fib again with the value n equals 3. Okay, so it gets its own stack frame with n equals 3. And, well, we compare n to 1, and we find that it's still not less than or equal to 1, so we move on to the next line and call fib of n minus 1, which is fib of 2. So we call this again with n equals 2. And again, we compare this to 1, and 2 is, where did this go? This is annoying. So again, we compare this to 1, and it's not less than or equal to 1. So we call fib again, this time with smaller value. And finally, we call this with n equals 1. So at this point, this is the first time anything actually gets returned. So far, all we've been doing is recursively calling this thing. And when we call it with n equals 1, what happens is we reach this point and we immediately return 1. So when we return from a function, we wipe its stack frame off the stack and we return this value 1. What happens now? So what's the next thing that happens in the execution of Fibonacci at this point?
Eliminate 2 and add 1.
Eliminate 2 and add 1? Well, we're back up now executing in this stack frame where n equals 2. And what have we done? We've called fib of n minus 1. And we still have to call fib of n minus 2. So we haven't done that yet. So that's what we have to do. And so we do that. So that means we call this fib of n with n equals 0. Well, 0 is less than or equal to 1, so this immediately returns 1. So this wipes off this stack frame and immediately returns 1. And now we add these two values together and return the result. So this returns 2. And this is off the stack frame. Now what happens?
You take 3 minus 2.
Yep. So now we return the fib of 3 minus 2, which is fib of 1, or we compute fib of 3 minus 2, which is fib of n equals 1. And that's one of these lucky ones that immediately returns the value 1. Now we're back up here in the stack frame with n equals 3. We add those two things together, and we return the result, 3. And now we're at the top level again, where we have called the first function. Sorry about this. I think it's actually that I have sweaty hands from running back and forth. Now we're back at the top level where n equals 4. What do we have to do now? Yep. We call fib of n minus 2, which is fib of 2. And we've seen how this plays out. This calls fib of 1. Which returns right away with a 1. It then calls fib of 0, which returns right away with a 1. It adds those two things together and returns with a 2. Finally, fib of 4 has the two answers it needs. It adds 3 and 2, and it returns 5. Okay. I think we did that already, but we can just check it. Fib of 4 returns 5. Super quick. Okay. Now, let's do this for fib of 35. And let's write the whole tree for that. Can we do that? Conceivably, if we had a bigger monitor, maybe we could do that. But why would it take us a long time? Yeah.
Because each time you call the Fibonacci function of a number greater than 3, it has to call that function again. So if you call for a really large function, each time we return numbers greater than 3, which will be twice each time.
Yeah.
You're basically making that tree twice for every number called.
Yeah, somehow the same trees keep showing up all over the place. So for example, if you look at this n equals 2, somehow we ran into it over here, and we also ran into it over here. And a little bit deeper, if you look at n equals 1, we ran into that here, we ran into that there, we ran into that there. And basically, so that means that, you know, n minus 2 is going to show up twice, and n minus 3 is going to show up 3 times, and n minus 4 is going to show up some number of times. But still not, that's a good clue that it's going to take a long time. But I want maybe to be more precise about that, more accurate about that. So look at these base cases here. So we hit these base cases at these bottom things here. These are called the leaves. Here, 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 and here. So how many of those base cases do we hit? 5. What's the value of fib of 4? 5. Is that a coincidence? Yep.
So only the base cases add values to your final answer.
Yeah. So somehow only the base cases add values to your final answer. These internal nodes here, so like these guys, all they do is take two things that were computed recursively and add them together. So they don't create any new extra value. All they're doing is adding up what came from the children. And so ultimately, the only thing that contributes to the Fibonacci number is what comes out of these leaves here. Now what comes out of these leaves is the value 1 all the time. In the base case, you only return a 1. So that means if we tried to draw the tree for fib of 35, we would end up with a tree that had about 1.5 million leaves attached to it. Yeah?
Not 15 million?
Is that 15 million? Yeah, 15 million leaves attached to it. So 15 million leaves on that thing. And then it would also have these internal nodes where there's these two recursive calls. Okay? So if we try to draw it, it will take us a long time. But that's also the same reason that it takes a long time to compute this thing. because ultimately what it's doing is it's computing the number 15 million by adding ones together. So it's taking 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1 15 million times. That's how it gets to 15 million. How can we do it faster than that? Yeah?
Keep track of values you calculated and do it while you're taking?
Yeah. So to compute fib of n, it's good enough to know the two values of fib of n minus 1 and fib of n minus 2. So maybe one of the better ways to compute fib of n is just to work in the other direction. Start by computing fib of 0, fib of 1, fib of 2, fib of 3, and so on. Because if we do it that way, then by the time we compute fib of I, we've already computed fib of I minus 1 and fib of I minus 2. So we can write this code fairly easily. Let's call it fast fib of n. So maybe we'll make an array, and let's say it's going to be start with a bunch of ones, and it'll have n plus 1 of them. So we create a list that has n plus 1 elements in it, and then we do something like for I in range 2 up to, but not including n plus 1, so I takes on the values 2, 3, 4, 5, all the way up to n. A at I equals A at I minus 1 plus A at I minus 2. And then we return A at n. Okay? So initially, we create this array and we fill it with ones, just because we had to fill it with something. And that means that A at 0 is equal to the 0th Fibonacci number, and A at 1 is equal to the 1th Fibonacci number. That's the definitions of those two numbers. Those are the two base cases. And so now if we start at A at 2, and we add the previous two values, which is 1 and 0, then we get the 2th Fibonacci number. Then we move on to the third one. We already have the two previous values. We add them together, we get the third one. And so on, all the way up to n. And at the end, then we get A at n. Okay. So we compute all the Fibonacci numbers all the way up to n this way. Seems like more work than necessary in some sense, but maybe this is faster. Okay. Well, let's think about this. If I try and compute fib of 35 now, then here if I do it, then I have to do about 15 million addition operations. How many addition operations do I have to do it with this second function? Yeah, it's going to be like 33 additions, right, of Fibonacci numbers. There's also a little bit of this subtraction stuff, but that appears in the other ones, the n minus 1 and n minus 2. But that, I mean, there should only be 33 additions. So 33 additions or 15 million additions, we can maybe guess which one is going to be faster. So fast fib of 35 is just instantaneous. And, I can even do fast fib of 350. There you go. And, I don't know, fast fib of 3500 is there. Now, there's no way we would ever get this with the recursive algorithm, right? I mean, this number, if we use the recursive algorithm, has to be computed by adding up a whole bunch of ones. Basically, 1 plus 1 plus 1 plus 1 plus 1 this many times. That's not going to finish in any of our lifetimes if we try and do that. So Python would happily do it. Well, no, it wouldn't be happy because of the stack height, but it would, if we increase the stack size, it would happily do it but of course the computer would die and the sun would burn out and everything else before it finished. Okay, so there's an example of a bad use of recursion. So you have this function Fibonacci, which is defined recursively, but it's a terrible idea to implement it this way. This trick here, to make it run faster, it goes under various names. It can be either called dynamic programming or memoization, but it's basically using the fact that if you compute this function recursively, you end up solving the same problem over and over and over again. And you could see that already in this tree when we tried to solve it for n equals 4. We solved the same problem for n equals 2 here and here in these two subtrees. So all that work got done twice, and you know, as n gets bigger, you get work that gets done more and more frequently. Okay. Any questions about that? It's clear why this is slow to do recursively, like not just a little bit slower, but I mean ridiculously slower. Okay. So the next thing I want to wrap up a little bit is an example of a good use of recursion, and that comes from a classic sorting algorithm called the merge sort algorithm that takes an array and sorts it. And it's really it is the guiding thing, you know, if you want to know what, you know, most recursive algorithms look like, what most efficient recursive algorithms look like, this is the thing. It's a classic divide and conquer. It says, take your problem, turn it into two subproblems, and recursively solve those, and continue, and then combine the results. Interestingly, Fibonacci is a little bit like that. Right? We had a problem of computing fib of n. We recursively turned it into two problems of computing fib of n minus 1 and fib of n minus 2. That didn't work out so well for us, but merge sort is going to work out a lot better. And the reason it's going to work out better is we're not going to sort an array of length n minus 1 and then sort an array of length n minus 2. We're actually going to sort an array of length n over 2 and another array of length n over 2. So if you're doing a recursive sorting algorithm, what's the base case? Yeah. Better than that? You can go bigger than that? One element. So if the length of the array is less than or equal to 1, then we're good. We don't have to do anything. Empty array is already sorted, and so is an array of length 1. There's nothing to be not sorted about it. So if the length is less than or equal to 1, then we return. Otherwise, we merge sort A. We do the following. We'll take everything up to position n over 2. We'll take everything from position n over 2 till the end. We'll merge sort A0, and we'll merge sort A1. So we've sorted the first half, we've sorted the second half. What's left to do? Yep. Concatenate. So do something like this. Return A0 plus A1. Is that correct? Let's try it. And let's try it on paper. So we'll take an array we want to sort. So I don't know, maybe A contains 7, 2, 5, 3, 1, 6, 9, and 8. So let's say that's our array A. So if we call merge sort on this array, we create this array A0. What's in A0? Yep. 7, 2, 5, and 3. And what's in A1? So this is the A0 comes from here. And then the A1 comes from here. Okay, so now we recursively sort A0. So what happens when we do that? Well, if this algorithm works, then what comes back is 2, 3, 5, and 7. And we recursively sort A1, and if this algorithm works, what comes back is 1, 6, 8, 9. And now we concatenate those two things together. So we get 2, 3, 5, 7, 1, 6, 8, 9. Is that sorted? No. So somehow concatenating is not the right thing to do. And if we think about it for a few minutes, we'll realize there's no way that this ever had a chance of sorting, because something we've never done is even looked at the values in A. We never even compared two values in A here to know which one is bigger and which one is smaller. So there's no chance of sorting. In fact, what happens if you run this algorithm where you just break it into two, run it recursively, and then concatenate them? Nothing. Nothing ever gets moved. So you get back exactly the same array. So what do we have to do then? Well, so, I mean, I still like this idea of relying on recursion to merge these, to sort these two things. But now what do we have to do? Yep.
Compare the elements.
Compare the elements. Which elements?
The elements in the array.
Compare them to what?
Each other.
Each other. So compare every element to every other element?
Maybe.
No. So we've already seen an algorithm that basically compares every element to every other element. That was the insertion sort algorithm. And its running time wasn't great. In particular, if you gave it an array that was sorted in the wrong order, it basically compared everything to everything, took forever. But I mean, let's work with what we've got so far. We already got so much for free from recursion here. Right? I mean, if this thing works, and now it's our job to make it work, then after we recurse, we have these two arrays, 2, 3, 5, 7, 1, 6, 8, 9. And now we're just trying to make the array, the final sorted array A. So how would you do that from these two sorted arrays? So what's the first element in A, in the final sorted array? 1. How'd you know it was 1?
Because it's the smallest.
Because it's the smallest. Is that because you looked at all the elements?
You just look at the first two.
You just looked at the first two, right? If there were thousands of elements here, it would still be okay for me to just look at the first element in A0 and the first element in A1, because the first one in A0 is the smallest one in A0, and the first one in A1 is the smallest one in A1, so the smallest one overall has to come from be one of those two things.
Yeah, but how do we sort the two, like the halves of the array in the first place?
Recursively.
But I thought we were trying to figure out how to sort it.
That's what we're doing. But if we can figure out how to sort it, then how to sort from these two sorted arrays, if we can figure out how to get the final sorted array, then we'll be done. Yeah.
So are we going to compare like A0, 0, and A1, 0?
Yeah, we're going to do a series of trials where we compare these two elements. Yeah.
So you find out which one's smaller. Does it just automatically put the next one in?
We're going to have to code that carefully. So, but the idea is we look at these first two elements here, see which one is smaller. That's the first thing that's going to go in A. And then we move on to the next element in that array that we just took it from. Okay. Now, the smallest element that we haven't output yet in A1 is 6, this next one, and the smallest one in A0 is still 2. So now we compare these two elements. We see that 2 is the smaller of them. Cross that out and move on to 3. Now we compare these two elements. We see that 3 is the smaller of those two. We cross that out and move on to 5. Now we compare these two, 5 and 6. 5 is the smaller of the two, so we cross it out, put it here, move on to 7. 7 and 6. 6 is the winner. Cross that out. 7 and 8. 7 is the winner. So we cross it out. And at this point, we have nothing left to compare 8 to, so we just finished with 8. Now there's nothing to compare 9 to, so we finish with 9. And we get our sorted array this way. Okay. So we have a plan for how to make this work. Let's just get it going. So we need a routine that can take these two sorted arrays, A0 and A1, and turn them into, and put them into A in sorted order, the original array. So I want to take two arguments, A0 and A1, those are the short arrays, and I'm going to put them into A.
So, wait,
Yep.
what if the first two elements were not 1 and 2, they were like 7 and 8 or something like that, right? And you wouldn't get the actual full sorted array, you'd end up with 8 being, or 7 being the front.
Well, so what do you mean if they weren't 1 and 2? Do you mean if they weren't the two smallest values?
Yeah, if the front values.
Well, if the sorting algorithm works, then they have to be the smallest values, because we called the sorting algorithm on that array, so the smallest values.
It's already sorted. A is already sorted.
No, A is not sorted. A started out looking like that, completely in weird order. We recursively sorted the two smaller parts, and now all we have to do is put those things together and get them into sorted order. Okay. If we can do this, this is going to work. It seems like a leap of faith, but just think of, well, how did those things get sorted? Well, they got sorted recursively. So they got sorted by breaking them into two parts that were not in sorted order yet, and then recursively sorting those, and so on, and then they got merged somehow. So we're still missing a link, this merge algorithm, but we know how it's going to work now. We're basically going to put a finger on an element in A0 and a finger on an element in A1, and compare those two things that our fingers are on. One of them, the smaller one's going to go into A, and then we'll move one of those fingers. Okay. So we need a finger on some element in A0. We need a finger on some element in A1, and we might as well also keep track of where the next element of A is going to go. And we do something like, well, not even. So these indices their names sort of say what they do. I0 is an index into A0, I1 is an index into A1, and I is just an index into A. So we want the smallest value, smallest of A0 at I0 or A1 at I1. Unfortunately, so we do something like this. If A0 at I0 is less than or equal to A1 at I1. So let's say A0 has the smaller value that we're looking at, then what do we do? Yep. We put it at the next place we're going to store something in the array A. So we're going to take A at I, and we're going to set it to A0, A0 at I0, right? So I is going to keep track of where we're putting things in A, and I0 is keeping track of things in A0. So what do we need to do with the indices now? Change them. Which ones do we need to change? Yep. So I0 needs to be increased because we just took an element out of A0 and put it in A. Now, turns out that we'll always be putting something in A, so we always want to increase the index into A. We just place something into A, we don't want to overwrite it in the next step, so we'll increment that. And then, of course, the comparison could work out the other way, in which case the element at position I in A comes from A1. Right? So we compare these two values. If the smaller one is in A0, we take it from A0 and increment the finger in A0. And if it comes from A1, we take it from A1 and increment the finger in A1. Is that going to work? Is that what we did here when we just did it by hand in this example? Yes? So, anything missing from there? We don't have to return anything because what we're doing is writing stuff into A. So we're returning it by modifying A in some sense. So this merge, in fact, this merge sort function doesn't return anything. It just changes the contents of A. But is this thing complete yet? Can you think of any other things that might happen here? Yeah.
There's only one element.
Yeah. So at some point you're going to get to the end of this thing. You'll have one element left to put in A. But where is it coming from? That means there's only one element left, so that means somehow we've already run off the end of A0 or we've run off the end of A1. And so it'll always happen that we empty one of those two things first, in which case we need to always take from the other one. And the easiest way to do that is just to check those things explicitly. So if I0 is equal to the length of A0, then we have no choice but to take from A1, and if I1 is equal to the length of A1, then we have no choice but to take from A0. Otherwise, only if we're sure that there's something to look at in A0 and something to look at in A1, then we'll do the real comparison of those two values. Otherwise, we just take from the other one. Okay, so if I0 is equal to length of A0, that means we took everything out of I0. So that means we should take our next thing from I1. And otherwise, if I1 has run out of things, we should take it from I0. Okay, let's give it a whirl. A equals. Okay, so A is not in sorted order. merge sort on it. Where did I use n? Right here. The length of A over 2, the length of A. And just so we're not always doing this, let's write a bit of test code here. Import random, A equals range 20, shuffle A, print A. Okay, so we printed A once, right after shuffling it, but before sorting it, and then we printed it again after sorting it, and indeed it comes out in correct sorted order. Okay, good. So it looks like we implemented this thing correctly. Any questions about that? Yeah.
What's faster, this or quicksort?
It depends on the implementation. They both have the same asymptotic running time, which we'll analyze quickly for merge sort. Quicksort is harder to analyze because it's a randomized algorithm. You need to know some probability, which we don't know yet. Okay, but I mean, let's see what kinds of numbers we can do here. So we saw that that Python is not good with large recursion depth. Yep.
Different sort algorithms work better on different types of lists. Like if a list is almost sorted, some algorithms handle it better. What kind of list is this best on, or is it pretty even across?
Merge sort doesn't seem to care much. It's maybe if you give it an already sorted list, it'll be maybe about twice as fast. And the reason is in the merge routine, it'll immediately run through all the elements of A0 and empty it, and then just tack on all the elements in A1 without doing any more comparisons. But that's two times as fast as nothing. That's meaningless. Change your programming language, it could run 10 times as fast. So that's not a big deal. So it doesn't take particularly good advantage of things that are already sorted. Something like insertion sort does take really good advantage of that, but insertion sort has terrible performance on things that are not close to sorted. So we know that Python doesn't like recursion depth bigger than 1,000. Is that something we have to worry about with this algorithm? So we could try and do this again and say A is actually a range of 10,000 elements. Is merge sort going to crash because of recursion depth? Nope. Look at the first 20 elements of A, and indeed they're correct. Can we do 100,000? No problem. Can we do 1,000,000? It'll take a few seconds, but it'll finish for us. There, it's done. So we can handle pretty big arrays. So it doesn't seem to be recursion depth, doesn't seem to be a problem, and running time also seems to be quite fast. So we can sort 1,000,000 elements in a few seconds using this implementation of merge sort. Let's try and understand this, and let's try and understand what this running time of merge sort really looks like. So we started with this example here, and now that we have worked through it a little bit, well, we can start with another one. So let's say I call merge sort on this array. So initially I call it on that array, which gives me A having 2, 5, 4, 8, 7, 1, 9, 3. And the length of A is bigger than 1, so I'm going to make these two arrays A0 and A1, which are going to have 2, 5, 4, 8, and 7, 1, 9, 3. Now what? What happens next? We call merge sort on A0. So we call merge sort on A0, which means we're calling this thing, this argument is 2, 5, 4, 8. Well, that still has more than one element, so we're still going to get an A0 and an A1. A0 has 2, 5, and A1 has 4, 8. What happens next? Yep. We call merge sort on A0, which A0 is 2, 5, which then is still has length bigger than 1, so it's going to split it into two parts. One part contains 2, the other part contains 5. Then we recurse, and finally we hit a base case where we have this array that has only one value in it, which just immediately returns right away. What happens now? Yep. So we're back up here where A has two values. We've sorted the first part of it. Now we're sorting the second part, which is A1. So this goes 5, and this, again, immediately returns. So we've returned from here already. This immediately returns. And now we call the merge routine to merge these two sorted arrays and put them back into to A. And so, what comes out of here is this sorted array, which actually didn't change anything, 2, 5. So A0 is 2, 5. And now, up here, we've sorted A0. Now we want to sort A1. That's going to proceed exactly the same way. We get A is 4, 8, which gets split into two parts. One part contains 4, the other part contains 8. We recursively sort the part containing 4. That immediately returns. So this has A equals 4, returns right away. We do the part that contains 8. That returns right away. And now we do a merge, which stores back in A these parts 4 and 8. So far, nothing has happened. But now we're back up in this function, where we have to merge these two sorted lists, 2, 5, and 4, 8. Well, when we merge 2, 5, 4, 8, we get 2, 4, 5, 8. So that writes into A, 2, 4, 5, 8. So what comes out of here is 2, 4, 5, 8. And now we're back up at the top. The first half is sorted. It's time to do the second half. And the tree for that is going to execute in exactly the same way. We get A7193, A071, and A1 is 93. Recursing on A0, we get 71, A0, A1, 7, and 1. A equals 7. A equals 1. These all return. We merge those two, and that writes back into A, 1, 7. So this A0 here now is a 1, 7. And finally, off to the right down here, 9 and 3, which sorts 9, and then sorts 3. It merges those two things to give you 3, 9. So now this is 3, 9. Now we merge 1, 7 and 3, 9. We get 1, 3, 7, 9. So what are we at so far? Up here, this is 2, 4, 5, 8. This is 1, 3, 7, 9. We merge A0 and A1 back into A. We get 1, 2, 3, 4, 5, 7, 8, and 9. Okay? So there's the whole execution of this thing when you give it an array of length 8. So, few things to think about here. How many leaves are in this tree? 8. Is that an accident? No. Because the base case is basically when n equals 1, in which case we get this little subarray of only one element, original element from the original array. So we get a number of leaves here which is equal to the number of elements that we have. So if we have n elements, we have n leaves. The length of A leaves. Okay. One level above that, how many of these nodes are there? Well, 1, 2, 3, 4. So there's half the number of elements. Okay, so here we have, so let's write this semi-carefully. We have n arrays or n subproblems, each of size 1. Here we have n over 2 of them. And how big are the arrays we're trying to sort in these nodes? Yep, 2. So we have n over 2 subproblems. Each one is of size 2. And up here, we have 2 of these things, which is actually n over 4 subproblems. And each array we're trying to sort has size 4. And up here, we have n over 8, which is 1 subproblem, and it's trying to sort the original 8 elements. Now, each of these boxes represents a call to this this merge sort routine. Now, how much work do we do in one of these boxes? So, for example, up here at the root, this thing of size n, how much work do we do here? So what do we do? Where does the work get done?
A0 and A1.
So we have A0, so we have to make A0 and we have to make A1. That means we take everything, the first half of the elements in A, and we copy them into A0. And we take the second half and copy them into A1. So we copy n values. So at something like this, we copy n values. And where else do we do work? Yep.
Well, on the way back up, then we have to sort the two.
We have to merge those two things. And so then we have to merge two lists of length, each of length n over 2. Or if you like, we make one sorted list of length n. Now, this merge routine, we can take a look at it. How many times did we go through this while loop? Yep. The length of 8 times, because this while loop says we'll go through it as long as I is less than or equal to less than a, and every time through the loop we increment the value of I. So we go through it exactly the length of 8 times. And there's nothing sophisticated going on in this while loop. It's just some simple if statements, maybe swapping a few values. There's no recursion or nothing that takes more than constant time. So basically we go through a while loop n times and we test a few things. So the work that we do is proportional to n, the length of a. Okay? So at this node here, we did some amount of work by copying these n values and then merging these two lists of length n over 2. We did some amount of work that is proportional to n. That's this thing here. Okay? So proportional to n. So at these two nodes here, if we know how long it takes to do the work that gets done at the root, well, what about the two nodes below it? How long will it take them? Yeah?
Same thing, right? 'Cause it's the half over half.
Yeah, so at each node, it should take half the time because that node has half as much work to do. It's not merging a list, it's not copying n values, it's actually only copying n over 2 values. And it's not merging into a big list of length n, it's only merging into a big list of length n over 2. So this should somehow take, this individual node should take work that's proportional to n over 2. But there's 2 of these nodes. So if you take their work and add them up, well, again, you get something, this plus this is something proportional to n. And now at the next level, the same thing happens. We have arrays now of size n over 4, so they should be 4 times as fast, but there's 4 of them. Yep.
So it ends up being like n times the amount of time you divide n by 2.
Yeah. So in this tree here, basically, if I, here I get n over 4, n over 4, n over 4, n over 4. If I add all that up, I get some work that's proportional to n again. So the same amount of work that it took me just to do the one node at the root, I can do all the 4 nodes at 2 levels down. And, I can do all the 8 nodes that are 3 levels down, and so on. So if I add up all the work that gets done, then I can add it up level by level this way. And at each level, the work that I'm doing is proportional to n. So all I need to know now is how many levels are there in this tree. Yep. Yeah. So somehow our working definition of the logarithm, the base 2 logarithm, is how many times can I divide n by 2 before I get something smaller than or equal to 1. And that's exactly what this algorithm is doing, right? It's repeatedly taking n, dividing it by 2, and recursing on that smaller thing. So you'll be able to do that log n times till you get something smaller than 1. Okay. Roughly speaking. There's a little small issue that comes along when you have odd integers n, and when you divide by 2, it's not a perfect split, but it's close enough. And so this is the idea. So the big picture of this thing is just exactly that the recursion tree looks like a big binary tree and so on. Until you get all the way to the bottom where you have a whole bunch of leaves that have only one node in them, and you have exactly n of them, and here you have one leaf, one node with this, 2 times n over 2, 4 times n over 4. The height of this thing is log base 2 of n. So when you add up all of this work, you get some work that is proportional to n times log of n. And the way we write that, instead of always writing proportional to, we just write this big O notation here. Some constant times n log n. Yeah?
Is that the fastest sorting algorithm?
N log n is the fastest sorting algorithm that you can have if you restrict yourself to algorithms that sort by comparing the values of elements. And by comparing, I mean asking if one is less than another. There are faster sorting algorithms. So for example, we can come up with one right now, but they only work for special inputs. So suppose I give you an array, and the array only contains zeros and ones. So I could run merge sort on that array, and I would sort it in n log n time. Can you think of a faster way? Count how many zeros there are, count how many ones there are, write out that many zeros, and then write out that many ones. Because in the end, that's what this sorted array is going to look like, a bunch of zeros followed by a bunch of ones. So actually, sorting integers, that's a trivial example, but sorting integers can be done faster than n log n, but notice that what you did there is not comparing values. In fact, you never even took two different values and compared them. You just, you compared it, you compared all the values to 0 or all the values to 1. So something funny, there's something different happening with that kind of algorithm. But if your algorithm works by looking at two things that are in the array, checking to see if one is bigger than the other, and it makes all its decisions that way, then you're stuck with this kind of running time. And so, we've seen these values of log n. So, if n was, about 1,000, then log n we saw is about 10, right? This was the guessing game that we did in the first class. We were able to guess numbers between 1 and 1,000 using only 10 guesses if we could do the arithmetic correctly in our heads. If you get up to 1,000,000, then log n is about 20. So that means n log n here is, 10,000 or 20 million. So the reason we could sort 1,000,000 elements efficiently is we only had to do about 20 million operations for that. That's not an unreasonable number of operations for a computer to do. It's a little unreasonable in the sense that, when we computed the 35th, or it wasn't even the 35th, was it? It was, one of the Fibonacci numbers, maybe the 35th or something, took about the same time as doing and sorting an array of 1,000,000 elements. So there you go. And if you wanted to go bigger, you could go up to 1 billion. And there you're only looking at about 30 as the value of log n. So you're looking at 30 billion comparisons or so, which is big, but remember, you're trying to sort a billion elements here, so it's only 30 times the size of the input. That's not crazy. I mean, if you have a computer whose memory is big enough to store those billion elements, you're already, I mean, that's already pushing the limits of what you're going to store. Yeah, so there's merge sort. One thing I want you to keep in mind is this tree here, and how we derive the running time of this by looking through the recursion tree. So, you know, we were given a recursive algorithm. It was not at all clear at the beginning how to figure out what the running time was going to be like, and the right way to do it, and the way we almost always do it, is, you know, draw the recursion tree for a small example, see what the shape looks like, and then usually from that you can start generalizing it to general values of n, not just n equals 8 here. So you can work things out that way and get, you know, get good estimates of running times. As a bigger guiding principle, this strategy of breaking the problem into things of 2 equal sizes, that's what we call just the standard divide and conquer algorithm, almost always leads to these kind of n log n algorithms. So if I can say the way I have to solve a problem is by solving the problem on the first half, then solving the problem on the second half, and then combining the 2 results. If I can combine the 2 results in linear time, then I'm laughing. I'll get an efficient algorithm like this. And first half and second half can mean different things. Like it might not be the first half of the array, but it might be all the values in the array bigger than something and all the values in the array less than something, as long as that gives you an even split. Okay, so I think that's probably a good place to leave it for today.